bx plus c. So let's check. Right, right. So let's go back. You said homework what? First homework?
Number 2.
It's not this one. So do you mean this homework too? Usually, general A, B, C, J, AX squared plus BX plus C can be used, usually. Any other questions?
If it's not quadratic, does that function still work?
No, only for quadratic we get these things because of the integration 1/3 comes. But if it is cubic, yeah, then cubic integrate becomes 1/4, things like that. Then it is different. What is your name? Okay, go ahead. We are interested in solving systems, especially EG systems called the linear systems. For instance, A11x1, A12x2, and then A1n xn equals B1, and AN1 x1 and AN2x2, and all the way up to this one, and then A and nxn equals Bn. So we want to solve a system like this, but the difficulty is not the idea itself, but the difficulty is the size of the system. We may have, for instance, 1,000 unknowns, 1,000 equations, this kind of difficulty. Then why do we have to worry about these kind of systems? Because in the real world problems, we usually break up the given domain to solve a problem. For instance, we want to solve some problem for this kind of shape. Then sometimes it's very difficult to really solve it in one piece. Then we break up. Then once we break up, then individual triangle has different equations. Then for each triangle, we may have one equation and another equation and so on. That means we have many, many equations to solve this kind of system. So knowing the method of handling this thing is very, very important. And in this course, we learn about very basic things. But there are more advanced things that I will just introduce instead of covering. But roughly, to find the solution to this kind of complicated problem, we break up, then individual piece creates one equation. Individual piece creates. In fact, in scientific computation, we cover these kind of things to handle PDE solving on top of this kind of shape. In any case, you will see the importance of linear system in the future too, even in this course. So as I mentioned, generally, the size of the system is something like this, right? Even 1,000 is very small system. So under this situation, what could be the best way? And we want to learn about the idea behind this kind of development. So last time I mentioned about Gaussian elimination, and Gaussian elimination handles the problem this way. Instead of writing down all the problems over and over again, just the coefficients are collected here. And so on, and then A1, and then the right-hand side is collected here. And the coefficients are collected here, and the coefficients are collected here. And then A, N, N, and then B, N, right? But for convenience, we also identify B1 as A sub 1, N plus 1, and Bn as A sub N, N plus 1. In other words, we consider N plus first column, right? We consider the right side as the next column. This way, we can simplify the description of the problem. Take a look. Essentially, we are handling the same problem. Here, we wrote down, take a look, xi plus, and all those xi and equals, all these things were here, but now we just extracted appropriate numbers, right? Numbers. And then we can simplify. So let's handle the matrix instead of the system. But essentially, matrix handling is the same as system handling. Then the Gauss idea is eliminating these numbers. And when we eliminate these numbers, there is a change. There are changes in each, right? There are many changes in each row, and there are different numbers involved in each step. And then after doing it, we remove all the numbers below, and we remove all the numbers below and so on. So eventually we remove everything down this line. So these things were mentioned last time. And if you have a question up to this point, ask me. Then the important thing is the implementation. How can you implement these things? We know the idea. How can you implement this thing? So this is the step. And I will open my lecture note, summary note, and then I will cut and paste that part instead of writing down formulas over and over again. So this is the summary note. So let's magnify these things and analyze these things together. Then so take a look. So by this simple algorithm, we can achieve the goal. So I will analyze this algorithm with you. This is not the actual code, but this will lead to actual code. So let's briefly follow the idea. First of all, we create the matrix that I described. We had n unknowns. But why do we have n plus 1 columns? Because the right-hand side, right, B1 through Bn became one more column, right? So we have n plus 1. So we have now a matrix containing the whole problem, right? Essentially the whole problem. Any questions up to this point? So a matrix contains the whole problem. In other words, when you are asked to solve a system, I will write down this, I will use this column to explain. When you are asked to solve a system like this, you should create a matrix A like this. A matrix is 5, 6, 4, 2, right? So you should create this kind of matrix. So you should convert the problem into a matrix. So the problem is given, then you create the matrix. This is the first step. The second step is eliminating all the numbers downstairs, right? Eliminating all the numbers downstairs, or eliminating these numbers. So this is the next step. So how can you do it? So let's follow the algorithm. So the next step is setting the pivot, and we use the first entry. We use the first entry, A, K, K. In this case, K happened to be 1, right? K is 1. So we pick A, 1, 1, and then create the multiplier. So this is what I do. I will write down the situation using actual example. Assume that you have 5 here, and you may pick any non-zero number here. What number do you want? You may pick your number. 2, x1, and so on, right? So assume that this is the situation. Then you find the multiplier, right? Multiplier of certain position, right? Of a certain position, and then equals 2/5. So you pick the multiplier. Then what do I do? What do I do? I multiply this number to the first line. I multiply this number to the first line. Then what happens? I multiply this number to the first line, then 2x1 plus 12/5 plus 8/5 equals 4/5. Do you follow me? So I multiply this number to the first line, then subtract this line from the second row. Then what happens? This will be cancelled, right? This will be cancelled. This way we remove the number below. So this is what the algorithm does. So I will return back to the algorithm. Before returning back, I will let you browse this thing and get the idea. Getting the idea is very important. Now I will determine this position. The multiplier is determined by the second row, right? By the second row. And then first column. So second row, first column should be used here. So row number, second row, right? Second row, and first column. First column is used here, right? So second row, first column is used. So multiplier will be determined many, many different times, and each time we indicate where the multiplier was determined. Second row, first column, multiplier was determined. Do you follow me? And the next thing is I multiply the multiplier to the first equation. This is multiplied to the first equation and then subtract. Yes, this is multiplied to this. So 5 and 5 cancel out, and 2. And so the definition, and I will return back to the definition very soon, but idea is more important. Once you know the idea, you will completely understand the algorithm. So let's return back. So take a look. We set the pivot, and then now take a look. AIK, in this case, it's a good idea to use actual number. So I will write down the number. Initially, k is 1, right? And then I is 2, right? K is 1. And then I is 1 plus 1, 2, right? This is the initial step. Then take a look. What is this number? This number is what? 2. What is this number? 1. So M21 equals what? M21 equals A21 over A11. So this is done. Right? First multiplier is found. I will magnify this thing. How? I don't think this program has magnification, so I will change the property. So we can determine the first multiplier by doing this. And if you have a question, ask me. Then let's go up to investigate one more time. So take a look. In the first step, we subtract multiplier times. We subtract multiply times this first row from the second row, right? So first row times multiply was subtracted. So that's what I will do. So let's do it. So multiply is first determined. Then now, what do? We change individual entry. We change the individual entry by subtracting the subtracting the multiply times first row from the second row. This is what I'm doing, right? So I subtract multiply times the first row. So this step is doing the subtraction like this, sorry, subtraction like this. Or more precisely, subtraction like this. 2x1 minus 2x1, something here minus 12 over 5x2, and so on, right? Subtraction is done in this pattern. But if you have doubts, ask me. So we go all the way through, right? We go all the way through. So take a look. We go from 2 to the last column, right? Second column through the end, right? Second column through the last column. You follow me? These represent the column number. Second column through n plus first column to do the subtraction. So we do the individual subtraction like this. So this number minus this multiply times this number is done, and then this number times multiply with this number is done, and so on. And then finally, this number time subtracted by the multiply times the number there, and then eventually we do the subtraction. So I'm just browsing the algorithm with you, but if you don't understand, you can create your own algorithm. And then afterwards, we now change the column number, row number. We handle the first row, second row, then row number should change, right? So after this, we should do the same thing with the third row, right? We should do the same thing with the third row. Then how can you determine the third row? We can determine the third row this way. Now we increase this I, right? I now become, after this loop, I now become the next number, right? The next number is 3. So now we are handling this thing with 3 because of this loop, right? Because of this loop. Then for this 3, what do? We do the same thing, right? We determine the multiplier. Then the next multiplier is what? Called M what? M sub what? M sub 3, 1, right? M sub 3, 1. And then it should be some number. For instance, if you have 7 here. Assume that you have 7 here. Then M31 becomes 7/5, right? 7/5. And the multiplier is determined. So multiplier is determined the same way. And then after multiplier is determined, right? M31 is determined. We now do the same thing from the second column to the last column, right? So we do the same subtraction all over those rows, right? I mean those entries in the same row. So this does the work, right? This does the work for the subtraction. And then after this is done, take a look. After this is done, then n is, in this case, 3, right? How many unknowns? 3 unknowns, right? So we are done. N is equal to 2. I mean, I is equal to 2, and I is equal to n happen to be 3, right? So we are done. Then what is the next thing? K changes, right? This K changes to what? 2. This K changes to 2, and we do the same. But before going farther, I will let you know one more thing. The superscript. Here I use superscript. Why did I use the superscript? The reason will be explained. The superscript is used to indicate the numbers. For instance, initial step, we had 1, 2, 3, 4, 5, 6, this kind of problem, right? In the first step, we had this kind of problem. Then I use superscript 1 to represent this kind of thing. But in the next step, what happens? In the next step, we change the number to these kind of things. Subtraction, after, what is the multiplier? 4 over 1. 4 is the multiplier. And then 4 multiplied here, subtracted. Then 0. 4 multiplied here, subtracted. 4 multiplied here, and then subtracted. Do you get it? Right? We get this kind of number. Then take a look. Initially we had A. But now we have A. But is the A the same or different? A are different, right? This A and this A are different. That's the reason I use superscript. So superscript follows the appropriate matrix in each step. But in programming, you don't have to really program this thing. This is for theoretical purpose. You can ignore the superscript in programming because you are changing the matrix anyway, right? You are changing the matrix anyway. You don't have to follow it. But in theory, we use superscript to distinguish the original matrix from the second one, and the second one from the third one, and so on. Each time we change matrices, right? So we want to follow this in theoretically. This is the reason why we use superscript. But in actual programming, you don't write superscript. In actual programming, you can completely ignore superscript. Right? You can completely ignore superscript. These are used only to explain. Any questions? Then the next step, K now, because we are looping, instead of 1, K now becomes 2. Because K is equal to 2, I should be what? 3. Do you follow me? K is 2, I is 3. Then the same way we can determine this thing. So the next thing that we can determine is, I will delete these things and write it. The next thing that we will determine is M, 3, and 2, right? K is equal to, I is equal to K plus 1, 3, and K is equal to 2. So M32 is determined. And we do the same thing. So I will describe these things using just shapes instead of actual thing. So initially, this is what we do. I'm not writing down the detail, but I'm showing you what happens. Initially, A is populated, right? A is populated by the problem. Then the part here determine the first multiplier, right? The first multiplier is determined. And it is recorded somewhere else, right? You don't directly use M something in the matrix. And then now, the actual thing happens here, right here, take a look. What changes? The thing that changes is this one, right? This one changes because of this. And then we go all the way through, right? We go all the way through. So this changes. And then I'm doing this loop, right? I'm now looping here. This changes, this changes, this changes, and so on up to this changes. Do you follow me? I'm just following the algorithm like a computer. So I determine M pivot multiply using this over this. And then after determining it, I don't even touch it. I just come to this one and then change all these numbers appropriately. And the next step, I go up and then increase this number to 3. That means third row, right? Then I determine this M multiplier, right? I determine this M multiplier. And then after determining this M multiplier, I do this loop to change all these things. I'm just indicating the change, right? I'm just indicating the change. And then now we increase this number to the next number, right? So we go all the way through to the end, right? To the end. So we do these things all the way to the end, right? I change these things. So initially we had A1 matrix, right? A1 matrix. But now this matrix is called A2 matrix, A superscript 2 matrix, right? A sup 2 matrix. So A1 matrix is gone. Now A sup 2 matrix is here. Then now take a look. What I do is this thing. Now we increase this K by 1. So K is equal to 2. Now we compare this ratio. We compare this ratio to determine M32, right? We determine M32, and then using this M32, I change the number. I change this number, right? I change this number, following all the way to the end. I change all the way through this way. So initial black one is A sup 1 matrix, and then red one is A sup 2 matrix. Now blue one is A sup 3 matrix, still being determined, A3 matrix. And then afterwards we do the same thing, and then we change this number, change this number all the way through. We are looping it, and then there are 2 loops involved, so we are looping it here. So we completed the loop. Then this is the A3 matrix, A sup 3 matrix. Yes?
If I start out with a system where I know that I have a 0 in the diagonal, I can start the problem by
Flipping.
Okay.
So, yeah.
If I do that, is there a danger anywhere in the code in which I might suspect or get a 0 someplace in there?
Generally, there is a danger. So that step is called pivoting, but because of the complexity, I omit that case. In other words, in this part, we don't assume that kind of bad case, but in reality, it can happen. Then what you do is this one. Before dividing, just before this step, we check whether this denominator is 0 or not. If this denominator is 0, then we switch the whole rows. Then we don't have this kind of trouble, but good observation. And the thing is this one, and then now K increase to the next number, then what you do is this one. I'm just indicating what we are doing. By using the ratio of these two, we can determine the multiplier, right? We can determine the multiplier, and then using the multiplier, we can change this one, all the way through, right? We change this one, and then change this one, and then change all the way through, right? We change this one and all the way through. So now you see what calculations are being done in this algorithm. So we go all the way to the end, right? We go all the way to the end this way. So each time we generate different matrix A. So A sup 1 is generated, then A sup 2 is generated, A sup 3 is generated, A sup 4, 5, 6, 7, and so on are generated. And now I will let you know one more technique, because for future purpose, it's not a good idea to leave some blank initially, I left this blank. Multiply was calculated, and then I left it blank. Instead of leaving this, I can just store this blank with the multiply that I got, right? So M21 can be stored here. And then M31 can be stored here, right? And we can store these kind of things all the way to MN1 can be stored. In the same way, we can store M32 here. M32 can be stored here, and then so these things can be stored here. Then later we can break up the matrix to get upper triangular matrix, right? To get upper triangular matrix, and then lower triangular matrix part in one matrix. So this is just one idea people developed. But this is not required at this moment. Just doing the calculation correctly is important. Then instead of just looking at codes or strange things, let's really run. Then you can really see. So I will create very primitive algorithm instead of sophisticated MATLAB algorithm to do it. But in my opinion, it's a good idea to use bigger resolution. MATLAB. Of course, MATLAB can handle this very easy because it can handle matrix multiplication, but instead of using straightforward MATLAB command, I will follow my algorithm. I will make the font size small so that I can write all the programs in one place. Gauss elimination, right? So I created this thing, and then let's do it. So A matrix should be given. So A matrix is, for instance, 1, 2, 3, and then 4, 5, 6. This means 1 times x1 plus 2 times x2 equals 3. And then 4 times x1 plus 5 times x2 equals 6, right? This is equivalent to some system. Then afterwards, I say this thing. For k running from 1 to, it's a little bit unlucky, but let's shrink it. I'm just writing this part of the code, right? Loop k1 through. So I'm doing this thing. And happen to be, in this case, 2, right? There are 2 unknowns. So I follow this thing. Now the second loop, for I from k plus 1 to n. And then now m equals a I do not know how to call it. For instance, K matrix is 1, 2, 3, 4. Then how can I call 3? K of what? Do you know how to do it? Right? This thing, right? So I now know. I'm learning to write IK over A, K, K. So M is determined, right? I'm exactly following each line using appropriate command. And then now we need the inner loop for j from k plus 1 to n plus 1, right? N plus 1. N plus 1. A I k equals A I j minus m times A k j. A k j. This is it. So I completed this programming. Done. So I completed the algorithm and then implemented it. If you have a question, ask me. If you don't, I will run testing with you and I check what is going on. The only thing that I didn't implement at this time is M. I just did M because M is used for the whole loop. You don't change M inside of this M instead of using MIK, but you can use MIK if you want in the future. So let's just follow this thing. So I will set a break here and run. And then you can see what changes here, what changes happen in the matrix you see. So let's run. I will open matrix A. So let's step. And A matrix is here, right? So I open A and then I will watch matrix A all the time. Please watch the change here. I use this arrow to move it out or move it in. So you can dock it or you can float it. Oh, first place, there were directory here, and I click on workspace. I someone told me. In any case, currently, this is A sup 1 matrix, right? It's A sup 1 matrix. Now you will see A sup 2 matrix. So A sup 2 matrix will be created. So each time, please watch the variable. Oh, this is bad. So let's dock it. So now I'm stepping it. So take a look. M is this side, right? M is this side, right? M is some number. So let's check what M is now. M is 4. Why? 4 divided by 1 is 4. So M is this side. Then the next step. Now it's time to really change the entry. So what position should change first? 2 to position, right? 2 to position should change. So focus on this 2 to position. Changed, right? Did you see it? And then now this will change, right? Now this will change. -6, right? It became -6. Did you see it? Then next step, it goes up, ends, right? But unfortunate to have this small size. I will increase the size because we are very sure that it works. So I will increase the size. So I increase the size, and then let's rerun it. So now A matrix looks like this. A matrix looks like this. Then let's do it. Oh, N is wrong. So let's set a break and then run. So we take the break, and then now it's time to run. M is decided, right? So first M should be equal to what? Can you guess what M is? What is M? 4, right? So let's check M. M is 4. And then, right? Did you see the change? Now 6 should become negative 6, right? 7 should become what? Some number, right? Negative 9. So I completed the change of the row. Then it goes out of this loop and then go to the bigger loop, right? Now new M should be determined. Can you guess what new M should be? If you look at these things, can you guess what new M should be? New multiply should be 1, right? So after this step, new M will be created, right? Calculate new M is 1. And then we go, and then now what will change? This will change, right? This will change, and this will. So this will change. So let's do it. Did you see the change? Did you see the change? So this is the A sup 2 matrix. From A sup 1 matrix, I got A sup 2 matrix. Now, we will go to the bigger loop. So take a look all the way, and then you go to the bigger loop, right? Now, take a look. New M should be created. So by this comparison, can you guess what new M should be? Negative 1/3 or negative 0.00033. It is already written here, right? Oh, I didn't suppress. It is already here. Then, now what will change? This will change and this will change. So let's do it. Did you see the change? Did you see the change? So this is it. So I completely changed the matrix, and as you saw, I didn't touch these things in the first place. I didn't touch this thing, I didn't touch this thing, I didn't touch this thing in the first place. So it's a good idea to use M's here instead of just the original thing. It's a good idea to use M thing here. But I didn't touch this thing directly. I only changed this thing and then this thing. I didn't touch this thing. So did you see the idea behind this? So I will make way bigger one and then just run so that you can just watch. So this is the 4 unknown matrix case. Oh, if 0 happens, then 0 over something is not calculable. It is not a number. Right. But I don't want to go into that area right now. So let's save it and then run it. So I did it, and then now it's time to really run. So it's very bad design. This kind of debugging command is somehow hidden if I don't expand enough. Maybe I can completely remove the pane itself. You mean this one? No. What I want to do is doing step by step, step over. But I don't see step over thing here. Then I should do step F10. I will do F10. Is that okay? F10. Yeah. So F10. So check. M change, right? M will change. So what will be the M? So you become computer and then check what will happen. What should be the M? Right? So M is 4. And then that kind of difference, right? So you see this thing, you see this thing, you see this thing. And then now new m should be determined. Right? New m should be determined. Do you guess what m should be? Because of this thing? M should be what? 1, right? M should be 1. M should be 1 because 1 over 1 is 1. Now, can you guess what will happen here? Can you guess what will happen here? So pure subtraction gives us 3 minus 2. That is equal to what? 1. This will become 1. Can you guess what happens? What will happen here? You don't guess? I somehow screwed, but that's matter. So we are doing this kind of calculation all the way through, right? So I finished the first pass. So a soup 2 is created. Now it's time to create a soup 3. Then, because of this number and this number, can you guess what will happen? What should be m? Right? Take a look. M is calculated, right? And then the number change. You saw the number change, right? And then you can see the change here soon. M is calculated, and this number change, this number change, and this number change. So we calculate. Then final step, we will change the remaining part, right? Remaining part, right? So we finished, right? So we completed this thing. Then take a look. We didn't change this thing or this thing, right? So we changed the things below, but we changed upper diagonal portion completely, right? Upper diagonal portion was completely changed. So this is what it did. So forward elimination completely removed the steps because all these are 0. It didn't even touch in the original matrix. But it doesn't mean these are not 0. These are all zeros, but there is no reason to fill these things with zeros. So in this program, it didn't even touch these things. Just regard these things 0. Regard these things as 0. And then just fill this portion. Any questions? So forward elimination is done. Then what about the next thing? The next thing is, after doing this thing, we assemble the solution by this simple algorithm. Just calculate the value xn, right? Calculate the value xn, and then use the value xn to calculate the previous value, and use the 2 previous values to calculate the previous value, and so on. So we calculate that. So I will implement this thing to my program to complete this task. So I will finish it. So debug and then continue. And done, right? And it's time to write the back substitution portion. The back substitution portion will be implemented right now. For k running from n to 1, right? N to 1 with each step minus 1. Oh, I guess this should be a command, right? Right? Decrease 1 each time, right? Decrease or increase -1 each time. And then x, I will say x is 0, 0, 0, 0, 0, 0, so that I can use, but it may be implicitly defined. A k equals 1 over a kk Do you follow me? I'm just copying this verbatim, right? 1 over a kk, and then now the next thing. multiplied by AK n plus 1 minus sum of AKJ AXJ, right? Sum of, but I don't know the sum command, so I will practice. Sum of I running from 3 to 5. Do you know how to add? How to add from 1 through? Do you know how to sum in MATLAB? In Maple, some command works, but in MATLAB, do you know how to sum? I will do that. Thank you. So what I want to do is implementation of this part. Of course, there is another method, but I want to find the natural one so that I can directly use it. Example. This is what I wrote down, but sum is not there. So I will make a sum on my own, right? On the fly, I will make a sum in usual technique. So usually, if we encounter this kind of thing, then it's a good idea to make sum, and then I call this T-sum, right? So T-sum will be created upstairs, right? Then this is it. Essentially, this is it, right? The determination of xn is done here. Only thing that we want is the T-sum part. In other words, I am just copying this verbatim. I'm copying this verbatim other than this part, because this part should be implemented. So I will call this part T-sum. Then let's calculate T-sum. So it is summing from k plus 1 to n for this combination. So please remind me, I will use my notes so that I can go these things, write these things without returning back and forth. So let's write it. I will write T-sum portion above this thing. Before calling T-sum, we should define this T-sum, right? So let's define T-sum. T-sum is initially none, right? 0. T-sum is initially 0. And then the next thing is T-sum equals T-sum for some unused letter. I will use, what letter didn't I use? W, right? For W. Running from, I used J here, so I will follow this same J. J running from k plus 1 through n. So J running from k plus 1 through. So I wrote down this part, right? K plus 1 through n. And then T-sum equals T-sum plus this part, AKJ XJ. AKJ XJ. That done. Sum is done, right? Sum is done. So please browse the idea and ask questions. Of course, I will run these things with you very soon. But initially, this will become empty. This will become empty loop because, take a look, k is n, right? N plus 1 to n by increment doesn't have anything. So it will be an empty sum. So this is an empty sum, right? Then this will still hold. It doesn't even go into this. I will show you. It doesn't even go into this because k is n, and then n plus 1 to n has none, right? Empty set. So it's empty loop. It doesn't even run. And then t sum equals to 0 is used here. Then essentially what it says is one. Xk is this number divided by this number. The right hand side divided by left side. That's it. Afterwards, something determined is used. Any other questions? So this is the back substitution portion. So take a look. I will run it. So let's break. Let's break and then run. So let's do it. Initially, this matrix is implemented here, right? This portion is implemented here. This portion is implemented here. This portion is implemented here. This portion is implemented in this row. Do you follow me? So do not miss the change here. N equal to 4, right? M equals this ratio, 4 over 1, right? And you will see the following change. This will change. And then you will determine this M, ratio 1. And then you will see the following change. And then you will determine this ratio. It should be 2, right? You will determine this ratio 2. And then you will see the change here, change here, change here, and change here. So you can do the same. So you already saw enough of forward elimination. And once we do the forward elimination, now we are at the backwards elimination step, back substitution step, right? But if you analyze this thing, it means this 0, x1, 0, x2, 0, x3 multiplied by plus 4.25x4 equals 82. So how can you get the solution for x4? This number divided by this one. So what this does is this number divided by this one. So let's follow it. T sum, and then as you can see, it's an empty. This is an empty loop, so you cannot even go in. So take a look at this pointer. It doesn't even go in. It's an empty sum. And then now, essentially, T sum is 0 because it didn't even go into this. T sum is 0. So 0 is subtracted, meaning this number divided by this number will be xn, xk, x4, I mean. So let's do it. Then this number is determined, right? x4 is determined. I initialized these things with zeros, but now x4 is determined. Then, now let's go to the next step. Now T sum, and then now, as you can see, we have decreased k. So k is n plus 1. I'm n minus 1. So n minus 1 plus 1 is n. So n to n is what? 1 number n. So it will go in or not? It will go in, right? It will go in. So once it goes in, then it will do this calculation to get some T sum number. So T sum is calculated. T sum is not 0 anymore. Then this T sum will affect the value here. Then this number is determined. Then now let's go up. And then now, as you can see, this k is now n minus 2. So it will go twice. And then T sum is calculated and then done. Right? Finally, T sum will be calculated 3 times, right? 3 times, and then do the calculation, and it ends. So we have found the solution. Done. So I completely showed the forward elimination and back substitution. Any questions? Then the next thing. So what we did was solving an equation, solving a system by doing forward elimination. Of course, I didn't fill these things with 0 in the programming. I already explained the idea, right? Fill these things with zeros. And then now after doing this, we do the back substitution to calculate xn, xn minus 1, and xn minus 2, and so on. So we do the back substitution to find all the unknowns. Then, can we describe these things in matrix language? And the answer is yes. I can describe the whole thing in matrix language. Gaussian elimination can be represented by this thing. I have a matrix A, x equals b in the first place. But now, what I have is this one. L times U matrix x equals b. And here, L is lower triangular matrix, meaning above is 0. And U is upper triangular matrix, meaning below is 0. What about the diagonal? Diagonal is 1, 1, 1 here. Diagonal here is 1, 1, 1, 1. Diagonal here is free. You can use any number that remains, right? You can use any number that remains after doing the elimination. So this is the LU part, decomposing L, decomposing A. So take a look. Once you look at this difference, only difference happens here. A became L times U. Because of this reason, the method is called LU decomposition, LU decomposition. But take a look. It is slightly different from the previous one. What is the difference? It doesn't involve the right-hand side at all. It doesn't involve the n plus first column at all. So in LU decomposition, you should reduce the number of columns. It doesn't involve the last column at all. It only decomposes the matrix A. What does this mean? It means this. A matrix becomes L matrix times U matrix, where L matrix satisfies this thing, U matrix satisfies this thing. So in fact, we could represent the Gaussian elimination using LU decomposition, but later, this is a remark, later people develop different So this is not the only way. This is not the only way to decompose a matrix into LU. But in this course, we don't cover different decomposition. We only cover this straightforward LU decomposition. Then, instead of talking about theories, I want to give you the example. Give me a matrix. Then, how can I make LU decomposition, right? So let's get to the point instead of wandering around. So what is L and what is U? By the pattern, I can at least write down many terms. 0, because it's lower triangle, right? And diagonal should be what? 1, 1. So the only thing remaining here is one number. And here, what is this number? 0, right? Because it's upper triangular. At least these much are known. Then let's determine the remaining thing. From Gaussian elimination, we can do it. So from 1, 2, 3, 4, I do the multiplier. Multiply equals 3 over 1 equals 3, right? So this is multiplied, subtracted, right? And then 3 multiplied here, subtracted, then negative 2. right? This is the Gaussian elimination. If you have doubts or questions about this Gaussian elimination, ask me. So Gaussian elimination is completed here. Then here, this directly comes to this point, right? This directly comes to this point. So it is 1, 2, -2. Then out of 8 numbers, only one number is missing. Only one number is missing. Can you find the number? I already wrote down the number somewhere. But can you relocate that number into this position? So where should we grab the number? Where? Where? Somewhere I wrote down. That's it. Done. If you doubt it, multiply. Of course, some of you are not good at head calculation or brain calculation, so I will use MATLAB to do the multiplication. So let's do it. Matrix 1, 0, 3, 1 multiplied by 1, 2, 0, -2, right? This is, do you follow me? I'm multiplying two matrices, right? Then what should I get? If this is correct, what should I get? Right, that is what? So I will hit the enter button. So take a look. Right? So this is the LU decomposition. So essentially this is the Gaussian elimination disguised. Gaussian elimination is done. Then during that Gaussian elimination, we recycle M. Right? We recycle M and store in the lower triangular matrix portion. And the completion of Gaussian matrix gives us the upper matrix side. So upper matrix side is right? Upper triangular matrix is obtained by Gaussian elimination. This lower triangular matrix is obtained by just recycling these numbers and then locating it appropriately. So if you doubt it, I will handle the bigger case. So instead of me picking the matrix, like setting up, I want you to pick a matrix of 3 by 3. Wow, it is really challenging, right, in hand calculus, but I will do it. So what number would you like? Excuse me? Please use number between 0 and, 1 and 9. Well, and then? So is this fair enough? Then let's do it. So you should know what is going on. First multiply is 3 over -1, right? Then it should be -3, right? So you know where to recycle. So instead of later recouping these things, let's just form the matrix. This is automatic, right? This is mandatory. Now, this -3 should be stored here. Where? Here. Then let's do the calculation. Then -1, 2, 1 is there, and then 0. And then this -3 multiplied and subtracted gives us 7. -3 multiplied and then subtracted gives us 8. Done. If you have a question, ask. Then the next step, M is what? Next step, M is what? 2 over -1. Then -2, right? -2 should be stored here. And then -2 multiplied in the first row subtracted. Then what happens? 0. And then -2 multiplied here. And then subtracted 10, 9. And then finally, we can find M here, right? M here is what? 10 over 7. Do you follow me? 10 over 7 is M. So 10 over 7 should be stored here. And then I will do the calculation. 10 over 7 multiplied in the second row and then subtracted gives us, instead of, I will rewrite it. I don't want to write. 0, and then 10 over 7 multiplied. So 80 over 7 subtracted from 9, right? Minus 17 over 7, right? Done, right? Take a look. It's an upper triangular matrix. So if you doubt it, I will show you the calculation of this product. Let's do it. But before going further, I will let you write down these things and then describe this thing. And all these are still stored in A matrix position, right? But in reality, this is A sup 1, right? And this is A sup 2, and this is A sup 3, right? This is A sup 1, A sup 2, but we don't use these things in programming, but in theory, it is A sup 1, A sup 2, A sup 3. The final thing that I want to do is multiplying these two matrices. So in fact, I used A, but A varies each time. So let's do it. It is 1, 0, 0, and then, what is the number? Negative 3, right? Negative 3, 1, 0, and then negative 2, 10 over 7, 1, right? A matrix done, and the L matrix done, and then U matrix. U matrix is right here, right? Negative 1, negative 1, 2, 1, and then 0, 7, 8, and then 0, 0, negative 17, 7. Then multiply. Take a look. We return back to the given matrix. So LU decomposition disguise is explained. Let's take a break until 3 by this clock and then resume.